Amazing. I think we're live. I think we're live. Here we are. It's Friday. What's happening? What's happening? Why is it saying I should? Yeah, cool. We are live. Screen flickered, and I didn't know what was happening there, and also it's showing the wrong window. So, it's been a long week. We've done like I think something like 8 streams this week, which has been really tough, but it's cool. It works, and I'm happy. Yeah. So actually, we're gonna finish off this week, and we're gonna do some simulation of this CPU that we've been building. For those who don't know, we've been building a CPU on the Arduino FPGA, and we've been building a tiny RISC CPU. My emails shouldn't show up here. Let me close this. Yeah, we've been building a tiny, one word, RISC CPU, not a tiny RISC CPU. I think tiny RISC might already mean something else. So I think what we're gonna do today is actually get the tests working. I'll show you the CPU code, and we can actually probably run it and see how it goes. So this is the CPU code, and all it does is we've got a clock divider over there. We've got a general purpose register, program counter, ROM memory, some wires to identify where we're going, and as well we've got like the main CPU running on every clock. And I think I can actually build it and run it just now, and then we will just go straight into simulation, and we can see what happens there. So let me build it. APIO build. I should ideally build, unless I was trying something. Yeah. And then I'll say iceprog, and then this is going to be in build, in underscore build hardware, or default hardware bin. There's nothing connected. Cool. Yeah. So let's do that. Let's flash something and see where we are going. Amazing. There you go. Actually, sorry. I usually do this when I show the thing. So let's go again. Yeah, there you go. Our CPU just goes through our code, and it blinks some LEDs on this FPGA board. This is the Arduino FPGA. Okay, so now let's actually check out what I wanted to check out in this stream. Over the past few days, I've been struggling. I think I've done maybe 1 or 2 streams where I've been struggling to write a test bench, a working test bench for my code. And after a couple of reviews from the guys at work, I managed to get a working test bench. And the thing I'm gonna do is I'm going to now, sorry about that. I'm going to now go to the test bench, and we can explore it. So I have something going on in this screen. And if you were here on the previous stream where we worked on how would I call it? If you were here on the previous stream where we worked on the test bench, you would know that I tried a lot of things and they didn't work. And then at some point I realized, like, instead of just keeping trying and stuff, I'm gonna actually go to work and get people to like review my work. Some people, we've got like a lot of people who write a lot of RTL or HDL code at work, and that really helps. So this is what I was given, and this is what works. I've tried to get it commented as much as possible so that I can actually walk through it with you guys here. Just a moment. So this is what is going. So let's actually just walk through it all through line by line, and then we'll go on. So the first thing we do is we set a time scale. And in Verilog, what this does, so let's open a manual along with that so that we know what is happening. Let's open a manual along with that. Okay. HDL, Verilog quick reference. Cool. It opened on the wrong screen. Here it is. So in Verilog, let's find timescale. Timescale. Let's see. What does it do? Specifies the unit and the precision. So this is like nanoseconds, I guess, and then that is like picoseconds, like be precise to within some sort of picosecond or something. I think that's what I'm presuming. So because I'm like a PS and a NS, and that's all. So basically here we are making a time scale of 1 nanosecond that is precise to 1 picosecond. I could be wrong. If I am wrong and you know this better, please correct me. Okay, cool. And then the next thing we do is we make a module tiny CPU TB, which is just tiny CPU test bench. And this is an orchestrator module. So this is a module that's going to accept our other module, and then it's going to implant some inputs. And then once it implants some inputs, it's going to run the normal operation of the other module. And then it's going, once it does that, it's going to observe the output of the other module based on what input it gave it. And so if you have like something like, let's say you have an adder function, you have a plus, let's actually write some code here. It's not going to work and it's not meant to. So you have some sort of function, it's say some add func, and then this function took like int a, and then it took int b, and then in there you went like something like this, and then you could close this. This is not going to work because this file is expecting Verilog and I'm not writing Verilog, and it expects that, and then you would say return a plus b, and then you can go ahead and make another function, add test. This one will take func adder, and then int b, and then it can even take an int c. Okay, int c, which is the total, and then you can run a function here which will expect. It says something like expect c is equal to a plus b. So adder a b. So this is just like some pseudocode here. All I did here was write some pseudocode. But what I'm trying to show here is that the function here, this is the actual function. This is our actual CPU in this case. This one is our actual CPU. And then in here, this is the test module. So it accepts the module you want to test and some parameters and does some assertions. And then in essence, that is actually what we're doing here. Actually, what we're doing here, this whole module we have built here is this whole module we're building here as a test bench is a module that accepts our other module, builds up with it, gives it some input, knows what to expect, and then watches it do the output, and then basically does it. So the first thing we need to do when we do this is we need to create some manipulation or orchestration data. And the orchestration data here is this register for the clock so that we can simulate a clock. And then we have these wires, LED red, LED green, and LED blue. And control A, control E. Okay, cool. D. Okay. Yes. Control E. D. R. Control Shift R. Okay. Control Shift R. Okay. Yes. Anyways, it doesn't matter. It doesn't matter because I can go back here and look at it. So here we have some inputs. We have an output for LEDs and an input for clock. And then in our test bench, we also have the same. We have some connections. We're not declaring whether they're inputs or outputs. We're just declaring that they're connections. And then what we do is we instantiate the tiny CPU module that we have on the other side. I don't know how I messed up my. Okay, actually, you know what? I do not know how I messed that up. How is that a buffer? How is that a buffer? Okay. Okay. Okay, cool. It's fine. We can do it from here. So what I want to show here is that the tiny CPU is this module. This module is the tiny CPU. Here you go. This is the module, the tiny CPU. And then so in our can I not use it? My computer today. So here we instantiate our module, the module that we want to test. And then we give it this clock wire or clock register that it can actually edit. We give it this LED red, LED green, and LED blue wires that it can put signals on. The CPU that we built can put signals on these wires that we give it. And then the next thing we go is we generate a clock. We generate a 50 megahertz clock. Okay, this is fine for now. And then based on that clock, we make some expectation variables to see. Like in the previous example that I wrote an adder there and I wrote a test for the other, I made like a C variable, which was supposed to be the variable that is going to be equals to A plus B. And then in the test module, we compare the result of the actual module doing something to those two variables, and then we do an assertion. And so these are just like parameters we're going to be using in our assertions. So one is for the cycle count, how many errors we do, and then we also want another one for slow clock cycles. Because if you realize, even though we do declare an input that is a clock, and we do use the input as a clock, we run the input here. The only thing we do when we run the clock, the actual clock, the 12 megahertz clock that's coming in, is we divide it by this is how many? We divide it by something like 2 to the power of 20. So we make it a much slower clock so that we can see this. And I can actually show you that. So show you the thing here. Let's go to this is Nathan's favorite part. Let's go to here and change this so that it runs on CLK, and you will notice something immediately. APIO build. So this is how the CPU behaves at the moment. You can see the colors changing, and you can also count. You can almost count seconds. And if I do APIO, actually not even APIO, if I just go iceprog hardware and I write in the new one, you will notice that the effect is that we don't have blinking. The reason it is actually blinking, to be honest. It is actually blinking, but it's blinking at something like 50 megahertz. And 50 megahertz is something like 50 megahertz is something like, what is megahertz? 1 megahertz. So one megahertz is something like 1 megahertz to it's 1 million hertz. I know it's 1 million hertz, but I wanted to show. Let's just do it. 1 megahertz to seconds. It's gonna be some ridiculous number, 0 point something. But what I'm trying to show is that 1 megahertz means it's blinking 1 million times a second. Megahertz, because 1 hertz is one times a second. Okay, 1 hertz is so 1 hertz. It should be something hertz. Yeah. So let's see the frequency symbol. The unit of the hertz symbol is a unit of frequency in the SI unit thing. And the thing I want to do is it means 1 per second. That's what I wanted to show. 1 per second. So when you hear 1 hertz, there's actually here. So here's a 1 hertz blink. I don't know if you can see them. And this is a 2 hertz blink, and this is a 0.5 hertz blink. So this one blinks. It goes 2 seconds and then it blinks once, and then this blinks every second, and then this blinks twice a second. So if you actually say 1,000,000 hertz over here, or 1,000,000 hertz over here, or here, then you start to see how many times this thing is actually blinking, but it doesn't look like it's blinking because in human timescales we cannot observe it going off and so. And so in our CPU here, in order to observe the thing, we use slow CLK. And slow CLK is the fast 12 megahertz clock divided by 2 to the power of 20. Yeah, it's a binary counter. If you find out how binary counters work and you observe this, you will understand how slow this clock is. So, anyways, let's go back to our test bench. So we have all of those observation things, and then now we want to do some stuff. So we use dump vars so that we can make a simulation file, which we're going to do next after we walk through this code. And I think I should pause for questions a bit. Do we have any questions? No questions so far. Cool. So dump vars enables us to make what is it called? Dump vars enables us to make a simulation to make a GTKWave file, which is the thing we're going to go to next. And that GTKWave file enables us to simulate this CPU. So there's a way we can write code and run that code without actually needing a device with us. All you need is APIO, which is the software that I'm using right now, or rather the build tool that I'm using, and it is APIO, FPGAs. So, and this is all you need. This tool, with this tool, you can write code and you can synthesize it and simulate it, and you can basically do FPGA development without an FPGA, which was quite the blocker for me because FPGAs are quite expensive. Okay, FPGAs are quite expensive, and I only got my first one I think this year, and that's when I got one, and hence we're building this at the moment. Okay, cool. So let's go back to our tests. Then we have a dump vars that actually dumps all the variables for waveform viewing. So it dumps everything it dumps all the variables that are in our CPU. Every variable you see here, all of this declared variable are dumped, so we can observe it later. That's actually quite insane that we can get that and observe that. So you can actually build things without ever touching hardware, which is cool. And then we give it some delay, and here we're using 100. I think that's quite a bit of time. That's like 2 seconds or something. I don't know. In computer time, seconds or microseconds, those are huge amounts of time. Cool. And then here we want to monitor the execution for a number of slow clocks cycles. So what we do here is we want to monitor it for 10 slow clock cycles, and which we watch for the slow clock rising. And as you can see here, we're looking at the device under test slow clock. So this actually refers to this slow clock over here, this one, okay, because it's a variable in this. And then we watch for every rising edge of that, and during that rising edge we're going to print the value of the slow clock cycles, we're going to print the value of the program counter, we're going to print the value of the instruction register, we're going to print the value of the LEDs, and then we do the same thing. We also display the register values for register 1, register 2, and register 3 and 4 and 5. This is the ones that we're using right now. Because we only have like 5 instructions, I think, if I'm not wrong. So there you go. So we have like 1, 2, 3, 4, 5, and then from there on, everything else is just noise. So we have 5 instructions, and that means it's going to use register 1 to 6. Register 1 to 6, not 0 to 5, because 0 is always 0 in RISC-V architecture. So cool. So here, during all of those cycles, we print the values of those registers, and then we see what they are. So we should have something like the slow clock, the cycle, and the register values, and the instruction register, and the LEDs, so we can know we can sort of surmise what is happening. And then we have some final verification. Now this is assertion. This is the thing that makes sure 1 plus 1 is equals to 2. If it's equal to 3, error out. So as we can see here, I'll show you control shift, control E. Let's see here. So as you can see here, we have some instructions. We have an add immediate 5, add immediate 3, add 5, the x1 and x2, which is 3 and 5. This should give us 8. Yeah, this is 8. Should be 8. And then I think this is and I, which is x4 and x3. This should be 0 because it should be 0 because if it's and, both of them should be set. But I don't think x4 is set. And I think this should be something like 9. Yeah, because it's an OR. x5. Okay, let's actually just run it all and see. We don't even have to try anything. Let's just run it all and see. And basically down here we have all the 3 assertions on register 1. So we check that the answer, it should be 5, and then it should be 3, and then it should be 5 plus 3. That is the entirety of a test. Let's run them. Let us run them. So let's see. APIO test. While it's running, because it takes a lot of time to run, I'll pose for some questions. Any questions so far? And it's running slow because we are using the slow clock. Ideally, we would probably use the slow clock during like run tests, like when you're running it on your desk, and then you'd let the computer run at its normal speed, which is whatever clock cycle you're feeding into it. It is not hung. Do believe me, it is working. It just takes a while. Actually, I can't actually fix it. Let's do this. Let's go here and then, but the problem is it will be out of sync. I don't actually have to have, let's see, CLK, and then, yep. Let's go here, and then we can go here, and instead of doing everything on slow clock, let's do everything on CLK. Just so we can get answers quicker, and then we can actually just keep going. We did get actually the answers. We actually did get them. But let me show you what the speed difference is. Hi PCB then. I'm using Yosis. I think. So it's gonna be one of this. So I'm using the APIO suite, and I end up synthesizing using one of the programs in APIO. So I think it's Yosis or something for synthesization. I believe it's Yosis. I could be corrected if it's wrong. I'm using Yosis. So let's actually run this test while it's fast, okay? And then we can see what actually happens. APIO test. And then you can see that when you actually use the fast clock, it's really fast. Yeah. And basically what this gives us is what is the instruction register value, what is the program counter value, what is the x1, x2, x3 register, and then we can see, like, okay, you can see here when you start it, I think x1 is 0, x2 is 3, but when is it? And yeah, x1 is 0. I think it skipped the first few ones because it's slow, but because of waited so long. But here you go. So we have 3 registers. So this is x1, x2, and x3. So that's 5, 3, and then 8. And then here we have 5 and 2, and then 8. and then here we have x1 and x2 is 5, it's 3, it's 8. It's basically just going through and looking at each variable at each clock step, basically. And in our results, we get what we need to get. And as you can see here, it should be 0 is 0. It should be 8 is 8 actually. It should be 3, it's 3. It should be 5, it's 5. So the next time we're going to be working on this CPU, and I think that's tomorrow or something, the next time what we're going to do is we're going to add a test. I think we're going to be doing store type or L type. Can you do L type before you do store type? I think you have to do L type so that you can load things and then you can actually store them later. So we're going to be doing L type. And the thing we will do is we will add some tests in the test bench, run them so we see them failing, and then we can go to our code and implement them. And that way, we know there's this verification we're going past. We're building code, but we're building it against some tests of some sort. And then, actually, the thing I wanted to show you is the synthesization. APIO sim tiny CPU testbench.v. Let's look at this. This is actually amazing. I love this. So what this gives us is basically we can watch our CPU in action. It's basically what we are. We can have the clock. There you go. We can have the instruction counter. There you go. Instruction register. We can have the PC program counter. We can have the frequency counter that we were using to slow down the clock. And then we can have func3, which we use for add. We can have func7 that was also in. We can have the immediate register, which is actually quite cool. I wonder how I can zoom in. I wonder if I can zoom in somehow. Can I actually zoom in? Control plus. I don't know how to zoom in Yosis. I don't know how to zoom in GTKWave. I will try and learn. And then we can have the last written register that we are using to observe the LEDs. And then we can have LED blue, LED green, LED red, and then the opcodes as well, and the destination register, source register 1, source register 2, and the slow clock. And basically what this enables us to do, as you can see, is, I'm sorry the video is, how do I say it? I'm sorry it's quite zoomed out, but if I could find an option of zooming. Can I zoom? Yeah. So basically, if I can find an option of zooming, you can see here, you can see that in essence, we can actually follow the execution of the program on the CPU. And we can see each value and what the value was at each point. And I think, to be honest, even though everything starts at 0, and then we can see the program counter goes to 1, and then we can see the frequency counter goes to 1, and then we see that this is the immediate register goes to positive 5, and this one goes to positive 3, and then we can go on and we can see the LEDs were off, and then at some point they come on. You can see at some point they come on. This one came on, this one went off, and such. You can really observe all the operations of your CPU as you're building it. And actually it's quite interesting because I happened to start FPGA development when things were already fast. Like this year, things were already fast. But my boss at work, he started FPGA development where it took them 40 or something like 24 to 48 hours to simulate stuff, or even to synthesize to synthesize. It's called a fabric or something. To synthesize it would take them 48 hours. It takes me so little time to synthesize, because within like a minute and a half I can deploy code on the FPGA and I can look at it, and even faster I can put it on GTKWave and I can observe it. And I genuinely think this is more of How can I do this? Can I escape or something? How can I make this not full screen? Anyways, I think it's quite interesting that in this time and age, we can do this, and this will give us a simulation like that. This is so interesting for me. Or we can do something like, we can do APIO build, and like that quickly we can build something, and we can already deploy it to hardware. It's still taking a while, but that's fine. Like, that was 2 sentences from me, you know. Any more questions? Hey PCB Den, we do have a Discord community. I think it's linked in the what do you call it? In the description of the video. Please join us and learn if you want. That would be cool. And teach us if you know more. We're not opposed to that. So let's actually just go commit the code that we wanted. So this is slow clock, slow CLK. I'll leave this as slow CLK for now. We will change from slow CLK the moment I learn how to implement delays, or if someone learns how to implement delays and puts it, because this thing is open source and it's already uploaded. If someone learns how to implement delays and can put them in before me, we can remove the slow clock and we can run at the natural speed of the CPU. So let's actually look this. Let's look at the change, git status. Git diff. This seems to be just me adding. Actually, this is a trick I learned. Whenever I didn't have default values for this, whenever I would run my tests, everything would be X and I would fail, and the test would fail. And I learned to put like default values or instantiation values so that it could help. So let's add that. Git add tb to the CPU. Okay, git branch. Where are we on right now? Git commit -m, and then we'll say add test bench. And then we can say add what? Default values for parameters. Okay. And then git status, git add tiny CPU, git diff dash staged. Let's look at this. So this is just a module that we walked through and looked at every line in. It's not very long right now, but I suspect as we go on and as we add more elaborate functionality in our test and something, it will go on and become more complex as we go. So that's it. Git add, git commit -m test bench, add a working test bench for our CPU. There you go. And then we can do a git push, and we can go and look at it on GitHub. GitHub.com tiny RISC tiny RISC. Oh, it's actually Zach tiny RISC CPU. And here's our CPU. Here it is. And what we just worked on right now is going to be on this branch. This one is going to have to be killed. Actually, it's actually quite awesome that this branch is still there, because this was my previous attempt at writing a test bench that failed. Yeah. Amazing. Any questions from anyone here before we can close up on this very fast, very Friday stream today? Any questions? Any questions? No? Okay. Thank you all so much for showing up. This has been an amazing session. Today was fast and easy, and it's really good when you get to the session and the code is already written. Sometimes it's not good, but today was cool, and we've actually struggled with that test bench for quite a while. So I think I'm quite happy that we've gotten it in, and the session for it was not as dramatic as possible, and I don't see why I should make this any more complicated than it is. Thank you all so much for showing up for today's thing, and have a nice weekend, Father. I'll see you guys tomorrow, where we'll work on some more stuff, and we'll do it. Thanks, PCB, then, for joining. Like I said, there is a link to the community in the description. Let me see. Yeah, there's a Discord link to the community. Join us if you want to learn this stuff, if you want to do this stuff, and like work with us. Thank you so much, and cheers. Thank you.